Thanks very much. It's been a pleasure to be here. It's really very nice to be in Japan again. I come a fair amount. My wife is Japanese, but it's great to be here and meet lots of scientists here, which I rarely do because I'm usually on holiday. So today I wanted to pick out a couple of topics from my research group, and they're shown here, if you like. One has just been mentioned. Both are thinking about how to scale up trapped ion systems. We've seen in the previous talk that that's a really major topic because the ingredients seem to be there for scaling, but at the same time, I think the methods for scaling still need some work. So one of the parts is an engineering approach. Can we use integrated photonics to deliver light to ions and get better control and better scalability that way? And then on the right-hand side, you see a new approach to doing the trapping of trapped ions, which has a very nice feature, which you see here in this picture drawn with a single ion, which is that we can scan the ions in 2 dimensions, which is something that's very hard to do in the normal ion traps. And I'll tell you more in depth about both of these approaches. So what you've seen from Professor Takashi is the description of the generic way that we do ion trap quantum computing. I think if you go to many talks, you will see these wonderful linear chains. And the basic idea is that this is a fairly fully connected system because it's a compressible system. It's sort of like a solid that you can push on a bit and squidge. And then we do that pressing with laser light. So we can pick to eliminate various pairs of ions, and these pairs of ions can then, with a suitable frequency of laser pulse, be entangled with each other, etc. So this is 50 ions coming from Rainer Blatt's group. And of course, this sort of platform has been very successful over, I think, 20 years. Probably this trap that this was done in is one that Ferdinand put into vacuum in the 1990s and still gets used in Rainer Blatt's group today. Yeah. So, of course, they've been successful in the context of quantum simulation, but they've also led to the launch of companies which can perform small-scale algorithms for you, and also early work on error-corrected qubits. This is also coming from the Innsbruck group, where they've done, I think, the first 2-qubit gates across 2 logical qubits. So, what's the challenge? The challenge is that the scaling we need for quantum computing is absolutely vast, okay? And though we can get systems which are linear, in, for instance, our system, we can get 110 calcium ions. We can keep them all weekend. That's no problem at all. In the end, what we need is logical qubits. And if I talk to my colleague in chemistry, he tells me, you want to get 1,000 logical qubits, and then I will fall into your arms. I can just do lots and lots of great things. Yeah. So if you can do that, that's where you want to be. But 100 ions is not 1,000 logical qubits. That's probably 1,000,000 ions. And so we have to think about how to split the approach up and modularize in order to scale up. And there's 2 ways we think about modularity in trapped ions. They've been mentioned already, so I'll go through them quickly. One is you break these long chains of ions into smaller chains, and you move them around to connect them. This is a bit like wires in a computer, but you're moving individual atoms around in your computer. And that's deterministic, so every time you move an ion, you go where you want, and you can know that you did it. And it also allows some nice features. For instance, you see the laser beams here are coming in parallel to 2 regions of the chip, and that's allowing you to parallelize the set of operations you do, which is more difficult in this many-body system of the huge long ion chain that you see at the top. The other approach, which is the approach taken in this Moonshot program, is to put these photonic links in place. This is, you can generate entanglement probabilistically there. Once you have the entanglement, you can use it to do further gates. So you have to have this factory always generating entanglement, which then is a resource for you to use locally. And I think most of us think in terms of a hybrid picture where, if you like, each of these red boxes is an elementary logic unit made up of some sort of quantum CCD, and these are then connected by fibers through these photonic links. But I should say that it will be very useful to make these quantum CCD units as large as possible before having to connect by the photons, because the photon part is relatively slow at the moment and probably remains relatively slow. You have to really generate a lot of these resource states as you're doing lots of gates. So it's helpful to make large quantum CCDs. And you can sort of see the challenge that might induce. What it means is I have to have lots and lots of electrodes that can control the shuttling of all of these ions, but also that I can deliver many channels of light to a chip sort of structure in order to control all of these ions, particularly if I want to make use of this parallel control. So let's have a look at the state of the art. The state of the art, to my mind, and many people might argue with that, is this continuum of device. I think actually, to me, this is the state of the art in quantum computing. They can evaluate, and the reason for it is they can do excellent gates, right? They can do 99.8 fidelity gates on any atoms that come together in a system, okay? So they have that wonderful thing, and it comes from the quantum CCD architecture. So you see, this is their chip. It's actually made as a loop of ion traps, and ions can be shuttled around this loop. It's like, they call it a racetrack, okay? And then the important regions where stuff happens are actually these 4 regions here, and these are where gates are done. These are the only places where gates are done. But any of the 32 ions that's in the system can be shuttled into these regions, and then laser beams are turned on, and that's where the gates get performed, okay? So what's nice about that from their perspective is they need to line up laser beams in 4 regions, which is a fairly limited number, and then they can recycle the use of ions through those regions, and they only really need to tune something up to 99.8% fidelity in a few, relatively few sites. So, what does that say? That says that at the moment they deliver light in free space to 4 zones. And is there any problem with that? Well, maybe. You can kind of see it from my very crude cartoon that the light flies everywhere. Okay, so maybe there's a problem in terms of controlling where that light goes. But the other thing is to say is that this is really a one-dimensional array of ions. It's a loop, yeah? And that is due to some fundamental reasons which I'll come back to later in the talk. That's, if you like, my 2 parts of my talk. One is about how to solve the problem of delivering light to many zones. The second one is about how to solve this problem of being in one-dimensional arrays. So let's think first about this optical wiring. And one of the great things that we have out there is the possibility to make use of technologies that are being developed for other fields. And one is these integrated waveguides. And the concept diagram, this is a picture from Lincoln Labs, who were the first people to do these sort of experiments, is that underneath the electrode layer, which is forming the electrical fields for the trap, is some sort of photonics layer which is wiring up the light. And then light should diffract out of that plane when it's needed to hit the ions. So you can see here and imagine a fantasy, if you like, but it's not too far off what we might imagine happening, where there are a bunch of these tracks where ions, above which ions are trapped, but then light comes out of these little windows and hits the ions and does the control. So that's what we want. And of course our dream would be that you just take a laser, you connect it to some fiber splitter, it goes through a set of modulators in some form, and then comes into the trap. The trap is here inside, in our case, usually a 4K chamber, and this is where the ions get trapped and dealt with. And right now we certainly get the feeling of this. So my students, we really have a laser that gets piped into a fiber splitter. We have a bunch of fiber modulators. Maybe that's not the most scalable approach because these are all little fiber modulator blocks on their own. They go into the 4K chamber and they do the control. So just a clarification that we weren't the ones to start this. This was started at MIT and Lincoln Labs. I think an idea even maybe coming from a PhD student in Rajiv Ram's group and then starting to talk to the folks in Ike Chuang's group and at Lincoln Labs. And I was lucky because the student Karameta then came to me for a postdoc. And he pointed to the challenges of the original work, and part of the challenge was just getting light into these chips with high efficiency. And doing that while being in a 4K chamber. So there was a 33 dB loss or something in light getting onto the chip from their free space delivery actually at the time. And that remained in later work of theirs where they've been able to actually integrate all wavelengths. So Karen came to me and he was determined to fix this problem and see if we could then use the extra power that we could get to do 2-qubit gates, which hadn't been done by these guys. So here's the chip that we used, okay, and this chip, you see here the gold surface mainly, okay, so here's the gold surface. There's a bunch of electrical connections coming here, which are the wire bonds, and the sort of novel feature that you won't see on many ion traps is this essentially a bundle of fibers coming in here and some sort of photonic connect that you see here. And we get the chips actually from a foundry. The foundry is Linux International in the Netherlands. And they make chips that look roughly like this. So they have a silicon substrate. There's some SiO2 layers. The important photonics layers are here. There's a couple of layers of silicon nitride. There's more SiO2. There's a ground plane, and that's really we drive radio frequency fields on these upper electrodes, and we don't want the silicon to see that. And at the same time, there's light and charges being activated down here, and we need to protect the ion from these charges. So there's two facets to that. And on the top, you see the electrodes, and the ions are actually trapped 50 microns above the electrodes. So, how does the light get there? Well, there's some structured patterns in the silicon nitride. These form diffraction gratings. The diffraction gratings are focusing gratings, and that takes our light to a sort of 3 by 7 micron spot, in this case, above the chip. The other thing you'll notice if you look carefully is that there are a couple of layers of silicon nitride, and actually that's a process which Lionix actually had developed prior to us getting to them. But it's very nice for us because when you're routing wires, you want a very tightly confined optical mode, and so there they can use some thick silicon nitride, but they can transfer on the edge of the chip to having very thin silicon nitride. The mode expands, and then we can just butt couple an optical fiber and we get good transmission onto the chip. So that's very important. It allows us then to get in a situation where we get good efficiency coupling, and it's fairly simple. So what to say about this? This is a sort of map of our vacuum system, and you'll see that there's a bundle of fibers drawn at these wavelengths here, which are compatible with silicon nitride. But at the moment, we're still using free space booms for some of our operations. Okay, so that's for anything in the ultraviolet. That sits inside a cryostat. There's a picture of the chip looking down, and if you look closely at the chip surface, you'll see there's actually here 3 different places where we can trap ions, and each of them have a pair of windows to bring beams to the ions. So, as I said, one of the main things was to reduce the fiber attach losses. We got them down to 1.5 dB. Remember the figure of 33 dB before, so this was a huge gain. Yeah, and this is a fiber attach loss that stays the same if we're at room temperature or we're at 7 Kelvin, which is roughly where we operate. So suddenly, instead of driving Rabi oscillations in sort of 10 microseconds or so, we have systems where we can drive it in 350 nanoseconds, and that puts us in the ballpark where we can easily do reasonable speed 2 qubit gates. And so just some sort of, these were our first results, if you like. We worked with about 1 milliwatt emitted from the coupler. We got gate times around 65 microseconds, and you can see just from, I'm not going to explain this whole pattern, but you just see that the contrast of this pattern is pretty high. And if we look at an interference fringe from this entangled state, we see that we get fidelities, or we got fidelities back then of around 99.3%. And I think the nice thing is that we understand it was a very raw gate in a sense. It was a single pulse. People know how to cope with some of these errors when they do multiple pulses. But in a sense, we could characterize all of the sources of noise. We understand them. The main one that's probably a problem, we see that in these traps, the heat is higher than we would like, and the motional frequency drifts are higher than we'd like. And some of that's associated with turning on and off light at different powers and things like that. So this is an extra complexity which comes with the new approach. But we were very happy that in a new technology, this sort of fidelity came straight out of the box. Okay, so what can you do with that? You can't just do the same old thing that you did before. You want to think about, can you do some cool science as well? And there's a few new features that are maybe available from these approaches. So one is actually to take one waveguide and split it in 2 and feed those 2 channels to 2 couplers. And that allows us to make standing waves above the chip. Actually, they're traveling out of the plane, but they're transversely, they're standing waves. And so we get a phase-stable standing wave aligned with the ion position, which is something that's not so easy to do when you have free space beams plus an ion trap. So just to show that, we've been playing with that. We're starting to look at 2 qubit gates in that setup. In fact, we've done some 2 qubit gates in that setup, but I'm not going to have time to talk too much more about that today. And then the other thing that's kind of intriguing, and I think Ferdinand's had work on this in free space in the past, is looking at interesting types of beams with interesting gradients. Quite often we use quadrupole transitions. They couple to interesting moments of the fields. And for instance, Gillen now, in the latest traps, we should be able to have interesting beams which can drive a quadrupole transition strongly but have no intensity at the center. And that could be interesting for atomic clocks and things like that, where you don't want AC stark shifts. So just following on from that, we've now been working more with 2 zones. So we started to use 2 zones. The painful part is the UV beams because we still have to align those, but the other part is just super easy. It's really nice to see. And so we've also set it up so that we can do multi-zone detection. You actually see 5 ions here. 2 of them are over here, 3 of them are over there, and we can do Ramsey experiments now where we do 1 pulse in one zone of the trap and 1 pulse in the other zone of the trap, and we see good coherence. Furthermore, we can start to do things parallel in 2 zones. It's really becoming a flexible system, and so this is really, I would say, is starting to demonstrate the technology which we really need for scaling. Now, the one thing that's missing, and I mentioned it just there, was that we still align these free space beams in for the blue. And actually, that's something we're solving in the next generation of chips, which I think arrived in Zurich as I was here. And what you see there is that there's a different type of waveguide that we're integrating, which is aluminum oxide or alumina, okay? And another thing to cope with some of the charging that we've seen, we're putting ITO, which is a conductor, but it's transparent on the surface of these traps. And one of the traps in that next batch is this thing here. Okay, so let me just describe it to you. One thing to say is it's got output couplers for all the wavelengths that we need, so we can think about scaling, okay? And the scaling we have in mind then is that at every one of these white dot positions would be an individual ion trap. And in fact, along this line is 5 ion traps, and we could connect all of those by shuttling ions in the RF approach. And so there are 4 of these 5-zone ion traps on a single chip, and we're hoping to put that into a system in the next year. So the fabrication on this is kind of beautiful. I find it amazing how good fab can be. And so one of the things Ionics have now done is to integrate really these grading couplers in alumina and silicon nitride into the same level of the fabrication. That's really a remarkable thing. I don't think I could try to do that myself. So there we are. That's actually the electrodes. And as I say, we hope these are coming into the vacuum in ETH fairly soon. Okay, so that's all about radio frequency traps. I would say nearly every experiment in quantum information that's been done so far has been in radio frequency traps. And now I want to convince you that we should not do that anymore. And I'll show you some recent results. So what are the problems of radio frequency traps? One of the major problems is that the radio frequency provides a tube. It provides a very good tube, and we like to sit at the middle of it. But if we go away from the center of the tube, we get a lot of micromotion, and this is bad for the laser-ion interaction. It's sometimes bad for stability of the traps. So 1D is nice, 2D is much more difficult to achieve. On the other hand, you can then fight it. Okay, you can say to yourself, okay, maybe I do gates in a 1D system, and then suddenly I take myself into a 2D cross. And people have operated these. In fact, Continuum had beautiful results recently from such a junction. They can transport with no heating, really observable. But there's a problem, and I think the problem is that at this point, or points around here, you do get a lot of micromotion, right, regardless of how you do it. And what that means actually is just a size constraint. So if you want to do your laser interaction regions, you have to pull them far away from where you want to do your junctions, okay? And this is just an intrinsic, I think, problem of these sort of approaches. So I think that's a problem. I also think a problem is that as we make bigger and bigger chips with more and more zones, they get hot. And okay, I don't think this was Sandia's proudest moment, so that they would probably not be very happy I share it, but in a sense it's just illustrative of a problem that's going to get bigger and bigger as the capacitance of these traps gets up. There's going to be more currents flowing and these chips will heat. So that's part of a problem with everything about RF, and I think we see it also in the photonics where everything has to be compatible with high voltage, more than 10 volts of RF at sort of 20 megahertz frequencies. That's really hard to combine with CMOS technologies and all of these things. Okay, so why not use penning traps? So what do penning traps do? They have a potential which is a static potential, right? And it confines along one direction, and you'll see that in this potential here, it anti-confines in the other directions. And while in an RF trap you get around that by modulating the potential, in the penning trap actually you use the Lorentz force. So you apply a magnetic field along the z-axis in this case, and then as you start to fall down the hill, you process around the side and you get locked in. So one of the nice things about that is you trap with only static fields, right? It's just static electric field, static magnetic field. So is that good for scalability? Let's see. Parent traps have been used in quantum science, so I neglected a few experiments when I spoke earlier, right? But they are of a very specific type. You'll see that one thing they allow you to do is to go into 2D, but with a couple of caveats. This is now in a situation where there's a global potential for all of these ions, and what that means is that this disk of ions is actually spinning around at about 60 kilohertz in order to keep it a flat disk, okay? And we don't want that for the quantum computing purposes so much because, well, we have to track this whole thing at 60 kilohertz, and we're back to the many-body system we had from the long ion chain. Okay? So our idea, and it follows work of others, and Ferdinand had some thoughts on this, I guess, well before us, but I think we've taken it a step further in a sense, is to just provide every single ion with its own quadrupole potential, but make now small enough traps that ions in neighboring potentials are Coulomb coupled and can talk to each other, okay, through the long-range Coulomb coupling. And then we just have to embed that in a global magnetic field, and every one of these quadrupole potentials turns into a trap for a single ion. So we imagine an array of microfabricated chip, if you like, with an array of ions on the top. And the critical things we need for that is we need to get the ions close together. To get them close together, you have to bring them close to the surface. And then we need that the heating rates are low. And what people have typically seen is that these scale pretty rapidly as you go close to the surface. So that's the worry. On the other hand, it is a flexible platform. It can be used in a sort of static manner for quantum simulation. There's an interacting many-body system sitting there at some level, yeah. But you can also think in a quantum computation context in a couple of ways of operating. And one is that because you've got local potentials, you can tune your potentials locally. So, for instance, you could tune two of the traps to one particular frequency, leave the others alone, and then you get graphs for the normal modes. This is normal mode number and frequency, where you see that there are well-separated normal modes, which are just modes of those two ions and not modes of the rest of the bulk. And then you can do gates on these isolated ions. So that sort of approach, I think, is also applicable to bosonic codes. Somebody mentioned I would talk about bosonic codes. I will say one thing, just that we like doing them, and we have a few results. But I think this sort of approach could be used in that context too, if you like. But typically, that's not the approach we take in ion trap physics. Okay, so we built one of these setups. Okay, the trap doesn't look like some massive array at the moment because we were worried, could we even trap in one of these things? Okay, so we just had to try. So it looks something like this. I think any ion trapper would probably say this looks like a pretty bog standard surface trap with these long electrodes along the axis and some other ones for control along the side. Our magnetic field is actually in the plane of the trap in this case. And we got that fabrication done by a group in Hanover, Christian Ospelkos's group, and it really is a very standard ion trap process. So I think the very nicest thing that we've seen in these traps is we're about 150 microns above the trap, and what we see is that the heating rates for the axial motion are extremely low. Okay, so just to say that in my group, the best heating rates we've had at similar frequencies have been about 10 quanta per second in most of our RF traps, and you see that this is about 100 times lower than that. So that's been quite a good boost. I'm not sure what that's due to. It may just be how well we do the filtering of the electrodes, but it's certainly, I think, a great start. Yeah? And it's quite amazing to have a system where you cool to the ground state, and after 1.5 seconds, you still only have a fraction of a phonon entering the system. Yeah. So I can compare that with RF traps across history, if you like. Hotmat Hefner very nicely makes up a whole spreadsheet of these so that you can plot them up. And you see our work is sort of, these are the axial results I've just been telling you about. These are some additional points from moving the ion downwards. Again, something that would be hard to do in a standard RF trap. And then here actually are the radial modes. But we've done that in two ways now. We see that that's due to injected noise because we have high noise when the ions are connected to the outside world, but because this trap is static, we can just detach it from the outside world. And then the ions just sit there, and then we see that the magnetron is actually then dropping into this range of the axial mode. So we think, again, that's very encouraging. It's kind of novel. It allows us also to think about these things as sensors of electric fields on surfaces and things like that, which I think is very nice. So now we think about another architecture for doing quantum computing in a sense, which generalizes, I think, the original CCD. So the original CCD, as I said, was all based on shuttling these ions around. In particular, one of the problems is you always have to go through these junctions where there's a lot of this micromotion. So in the penning trap, that doesn't exist. The magnetic field is homogeneous, so anywhere you move your quadrupole center of potential, you can just move it arbitrarily. And you're not constrained by having two microscopic potentials that you have to line up with each other. You just have one, which you can move in a uniform field. That's very nice. So you can transport at any position. And then we were able to show this. So actually, this is a picture where we take a single ion, we cool it, and then we move it somewhere else, do a detection, move it back, and we raster up this image, which is showing that we can move into 2 dimensions, right? And of course, the students enjoy writing ETH. ETH at the moment is limited in size by the size of the laser beams, by nothing else, really. And also, they like doing things like the Swiss flag, and somebody's girlfriend was Austrian. We had to have the Austrian flag, and yes, that's the way it goes, yeah. So I think it's very nice as a start. We have to do more ions, of course. We've got a lot of things to do. But this concept of having static fields is really nice in the sense there's no power dissipation at all. I think that's the only atomic system where the traps don't involve power dissipation. So in a sense, the trapping is scalable, yeah? And it's the first time I could conceive of making a trap where I think, oh, maybe I just make a huge array. 1 centimeter squared, 100 micron pitch, that gets you to 10,000 ions. Maybe you could have 10,000 ions on a chip. I think it's a serious prospect, you know. So this I'm looking forward to trying. Yeah. Good. So where can we go? Well, we could combine the integrated optics and the penning traps, right? We've got this wonderful trap that, in a sense, is 4 5-zone linear traps. All of a sudden, if we stick it in a magnetic field, it becomes a 20-zone fully connected penning trap. So I think it would be great if we can get to that situation. And we'll have to switch to calcium ions to do this. We're currently using beryllium, but this is a change that we can make. We probably need another magnet. So if anyone has money for another magnet, just tell us. Yeah. Good. So with that, then, I thank you for listening, but I also thank the team. I think the initial team on the integrated optics was particularly led by Karan Mehta, who's now a professor or assistant professor at Cornell. Maciej and Chi have also moved on. In the integrated optics team at the moment, we've got some great PhD students, Alfredo and Gillen, and Carmelo as the postdoc. And the penning trap team is also going great guns, really. Tobias and Schwenz are superstar students, really good. Yeah. So thanks for your attention, and I look forward to any questions you... Actually, I've missed some name, and I need to say this name, and I didn't mean to... We had a wonderful student from University of Tokyo, a 30th student, Yuto Motohachi. He's been working on the integrated optics team, and actually his name was on the 2-zone type stuff. He was really critical to that. He did a wonderful job. We're trying to beg him to come back for a PhD. So you guys produce great students. We're very happy to see more of them. Thanks very much.